Hi, this is Rohan from educator.ai. Let's dive in. Every large language model you have heard of, the ones that write code, answer questions, summarize documents, is built by stacking one simple part over and over. That part is the transformer block. In this video we build it from the bottom up, so you know exactly what happens between the words you type and the answer that comes back. As a developer, you can call a model with one line of code. But what is inside the box? Text goes in, a prediction for the next word comes out. In between is a tall stack of identical layers. If you understand one of those layers, you understand the whole model, because they are all the same shape, just repeated. Here is the mental model. Imagine your words riding on a conveyor belt. Each station looks at the entire line, lets the words share information, and nudges each one to carry a little more meaning. Nothing is finished in a single pass. Many identical stations, each adding a small refinement, turn raw words into a rich understanding. First, the text is chopped into tokens, chunks of characters, often whole words or word pieces. Each token maps to an integer ID from a fixed vocabulary. So the phrase becomes a short list of numbers. This is the raw material that flows onto our conveyor belt. A bare integer means nothing to the math, so each ID is looked up in a big table and replaced by a vector, a list of numbers that lives in a space where similar meanings sit close together. We also add a position signal so the model knows which token came first, second, third. Now every token is a point in space, ready to be refined. The first stage inside a block is attention. Every token looks at every other token and decides how much to listen to each one. Here the word sat attends strongly to cat, because knowing who did the sitting changes its meaning. Attention is how information flows sideways between tokens, mixing context into each vector. Attention does not replace the vector, it adds a correction to it. We take the original vector, add the attention output on top, and then normalize the result to keep the numbers in a healthy range. That keep the original, add the change trick is called a residual connection. It lets information skip past the layer if it needs to. Why bother adding the input back? Because when you stack dozens of layers, the training signal has to travel all the way down without fading. The residual gives it a clean highway to flow through, and the norm keeps the numbers from exploding or vanishing. Without this pair, deep transformers simply would not train. After tokens have shared context, each one goes through a feed-forward network, a small two-layer neural net applied to every token independently. Attention lets tokens talk to each other. The feed-forward lets each token think on its own. It too is wrapped in add and norm. And that is one complete transformer block: attention, add and norm, feed-forward, add and norm. Let's name the rhythm clearly. Mix information across tokens with attention, stabilize with add and norm, refine each token with the feed-forward, stabilize again. Those four moves together are one transformer block. Simple, repeatable, and always the same shape. Now the key idea, we don't use just one block. We stack the identical block n times 12, 48, over 100 in the largest models. Each layer refines the vectors a little more, so early layers might capture grammar and later layers capture meaning and intent. That's what the little times n bracket means. The same recipe, repeated to build depth. At the very top, the final vector for the last token is multiplied by an output matrix to produce one score for every word in the vocabulary. Those raw scores are called logits. Run them through softmax and you get probabilities. The models guess for what comes next. Embeddings in at the bottom, logits out at the top. Two numbers largely decide how powerful the model is. Depth, how many blocks you stack, and width, how many numbers each token vector carries. Turn both up, and the model can represent more, but it also needs far more data and compute to train. Depth and width are the capacity dials of a transformer. Here is a tiny transformer block in pure numpy. 3 tokens, each a 4-number vector. We run attention, add the input back, normalize, then a feed forward with a ReLU in the middle, add and norm again. Notice, the output has the exact same shape as the input. That is the whole reason blocks stack so cleanly. Each one takes vectors and returns vectors of the same size. A few traps to avoid. Attention and the feed forward do different jobs. One mixes tokens, the other refines each alone. Don't blur them together. Add and norm is not cosmetic. Remove it, and deep models fail to train. And although every block has the same shape, each one learns its own separate weights. Same architecture, different knowledge. Line up the right picture against the common mistakes. A block is attention plus feed forward, each wrapped in add and norm. You stack n of them, and the shape never changes. Residuals are what make depth trainable, and the top projects to logits raw scores not yet probabilities. The buggy column is where beginners slip. One block is not the model. Blocks don't share weights, and normalization is not optional. So here is the whole picture. One transformer block is attention, plus a feed forward, each wrapped in add and norm. Stack that identical block n times to build depth. Token embeddings flow up from the bottom and come out the top as logits. And depth times width sets how much the model can learn. Understand one block, and you understand the engine inside every modern LLM.